First of all, you are welcome here to Pure Aqua. We're going to start talking about the product line that we have. We're going to divide this one into 5 different categories. The first one, we'll talk about the reverse osmosis. The second one, we're going to talk about the filtration. And the third one, we're going to talk about the ion exchange, water softening in particular. Then we're going to talk more about the disinfection, the sterilization by ultraviolet sterilization. And then at the end, we're going to talk about other products, different products that we have. So now, the first session that we're going to start with is the reverse osmosis system. Now, the reverse osmosis technology, it was invented like 50 or 60 years ago, and there's a lot of research that developed in the past, in particular the last 30 years. A lot of improvements, a lot of development happened in the last 30 years. The membranes, which is the core of the reverse osmosis technology, that's what it rejects or reduces the TDS in the water. The TDS is what represents is the total dissolved solids, the amount of ions available in the water, whether it's positively charged or negatively charged. And both of them, they have to be equal. So that's what we call balanced water analysis. Now, some ions, as we know, they're like big ions. Some ions are medium size, and some ions are small size. Of course, rejecting the small ions are really challenging, and that's the most difficult things. Example, seawater, as we know, it has like about 90, maybe 97 or even a little bit more % sodium chloride. And we know sodium chloride, both sodium and chloride are very small ions. We call them like monovalent. Monovalent means the little ions that they require very thin, small holes. We call it in the water terminology like high rejection membrane. High rejection membranes are, the holes in the membrane are really, really tight. So that requires a lot of pressure to push the water to be able to reject those ions, and the pure or the permeate water passes through the membrane. So that's what we call rejection. In the membrane development in the past 30 or 40 years, like what we said, like it developed a lot. Like maybe they started with 95, 93, maybe even 90% rejection. Now we're talking about 99.8% rejection. Now, a lot of uses for the reverse osmosis besides like seawater desalination. So many new applications that happened in the past years, including the reclaimed water technology. So you take the wastewater or the sewage water, they're preliminarily treated with like MBR or like conventional wastewater treatment or any other technologies like RBC, and then they take it from this basic or preliminary treatment to the reverse osmosis. Somebody would ask, why do you have to take it through the reverse osmosis? Now, the reverse osmosis, the good thing about it is it's not only like rejects those ions, it's an excellent filtration for all types of viruses and bacteria and organic matter. It's very safe for people to drink the water after the reverse osmosis. Now, example, like whatever, if you go to different countries in the world, like they have volcanoes, rocks, mountains, whatever, whether it's above the ground or underground, those rocks keep generating like some nuclear, like pollutants, I want to call it. Now, or it could come from something else, like because of wars or whatever. Now, the reverse osmosis would also reject those ions, which is basically the rhenium and the uranium from the water. So this is really, really another big advantage of the reverse osmosis technology. Besides that, like other advantages of reverse osmosis technology where we can use it, you can use it in a lot of different applications, starting from the pharmaceutical, the medical, drinking water, reclaimed water treatment, for irrigation, for painting, for chemical processes, for manufacturing processes, a lot of applications. Whatever, the bottom line is, whatever you need a good water, you can use the reverse osmosis. In addition to that, some industries, they would require double pass reverse osmosis. Double pass reverse osmosis means we take the product with the first RO, we take it to a second RO. Somebody would ask, why do we need something like this? Some industries, like pharmaceutical and like, let's say, power generation, they would really require ultra pure water. Sometimes if you want to wash the circuit boards, little things like if the water has some ions, whatever, it makes a noise in conducting some electricity or whatever. So it makes the product itself failing. So they need to wash those boards, or they need to provide good quality water for the boilers, for the washing, for any process that we're going to talk about soon. Now, to answer the question, why do we need double pass reverse osmosis? Because, like what we said, some industries, they would require ultra pure water, where the quality of the water is really, really important for their process or for their product. Let's take an example of pharmaceutical industry. Now, when we talk about manufacturing some medicine, we know that there are a lot of different types of medicine. Some medicines, it's being used for the internal body use. Some of it, it's just you swallow by stomach. Some of it, it goes with the blood. Now, anything that goes, when you swallow it, the treatment shouldn't be maybe double pass RO. Regular thing would be fine. Now, if it goes with the blood, this is really crucial. So, example like the hemodialysis or the kidney treatment. Kidney treatment, the water has to be Pyrogen free. What does the Pyrogen mean? Pyrogen means when you treat the water or when you disinfect it with UV or ozone or whatever, you can end up having some dead bacteria. It's dead. It's not going to harm you. But it's bad if it goes inside the body. It makes some side effects. It causes fever. It causes a lot of problems with the body. So how can you get rid of the Pyrogen? The good thing is, of course, reverse osmosis would get rid of those things. There's another way, let's assume that you have an RO and you put it in a tank, you store it in a tank, and then you leave it for 1 or 2 or 3 days, whatever. You're going to start getting bacteria again if you don't treat the water the way it was supposed to be. So, but now it's going to be easier to treat because the water doesn't have any TDS. So you can take it to a UV sterilization, then you can take it to something called 0.2 or 0.1 micron biological filter. That takes care of the Pyrogen or the bacteria, which is what we call the dead bacteria. Another example is if we talk about boilers feed. Some boilers are really, really high pressure. You would save a lot of chemicals when you do the blowdown and when you clean those boilers. So you would at the end save a lot of energy by providing good clean water. Now, let's talk a little bit about the different types of reverse osmosis based on the feed water. So we're going to classify the water types. If I'm going too fast, please stop me. Now, we can categorize the water like tap water. Tap water is anything that has a TDS. TDS again is a total dissolved solids, 1,000 ppm or below. That's a definition. It could be a different number from one person to another. But most of the industry, they would define it as 1,000 ppm or less, which is whatever we see worldwide, about 1,000 ppm of TDS or less. The second one is brackish water. Brackish water means a little bit salty. The water most of the time comes from underground, or it could be from lake, or it could be from river, where the salinity is a little bit high. The definition of the TDS here, or the parameters or the range, is between anything higher than 1,000 to 5,000 ppm, milligram per liter. Now, according to the WHO, Water Health Organization, anything more than 1,000 microsiemens, sometimes 1,000 ppm, people they say, it should be treated. Then it's going to make some harm to your body. So water that you drink, it should be lower than 1,000 microsiemens. Why we say that? Because the water is used for what? We know that more than 70% of our body is water. So the water that you need to use for flushing or humidifications or cleaning your body for all the water that goes to the liver, to the kidney, it has to be clean. If it has high TDS or salinity or whatever, it's going to make a lot of problems with your kidney and liver. Now, we said that the city water or the tap water, 1,000 ppm or less. We said that the brackish water is between 1,000 and 5,000. There is something that we call highly brackish water, which is what's between the brackish water and the seawater. This goes between 5,000 to 10,000 or a little bit higher, no problem, ppm. So that's what we call highly brackish water. The last one is what we say seawater. Seawater also varies between one country to another. If you come here like to the Pacific Ocean, it's about 30,000 ppm, 29,000 in some areas. If you go to the Northern Sea, it's about 19,000. If you go to the Black Sea, it's about 15,000. If you go to like Mediterranean, it's about 36,000. If you go to the Red Sea or the Gulf in the Middle East, we're talking about 45,000 ppm, which is really the most difficult water to treat. Now, the higher the TDS, you need more pressure to force the water to pass through those membranes. So to be able to reject the sodium and the chloride and all those small ions, you need to push the water harder and harder. So the most expensive thing in the seawater reverse osmosis is the energy. Now we'll talk more about the energy. Now, how can we save energy by using some energy recovery turbines or devices where we can save at least 40% of those of the power consumed by the RO. So now this is the definition that we said about the water source, which is tap, brackish, highly brackish, and the seawater. Now, what other things that we need to look at before we think like whether the reverse osmosis technology is good to use or not? Of course, TDS is the first one. Now, if you come and tell me like, oh, I have a water that has 70,000 ppm or 80, I would tell you, no, reverse osmosis is not a good technology. So it's good for like water up to, I don't want to say good or bad, it's feasible, up to 50,000 ppm. Now you need to look at like treating the water before it goes to the reverse osmosis. Again, reverse osmosis membrane is used for like desalinating the water. Means taking whatever dissolved in the water. You don't want to use the reverse osmosis to remove iron or to remove manganese or to remove suspended solids or to remove turbidity from the water or to remove oil. This is all wrong. You can't. You're going to foul the membranes like within a short period of time. Reverse osmosis is good to reduce whatever dissolved solids available in the water. When we say dissolve, like sodium, chloride, potassium, bicarbonates, sulfates, all those things that are really difficult to remove by other technologies, which is really the most difficult things. Now, reverse osmosis doesn't like any heavy metals like iron, manganese, before the RO. So we need to get rid of those before those. And those are easy to filter out, no problem. No oil, no grease, no organic materials like no bacteria, no viruses. As much as we can, we need to get rid of all those. BOD and COD, we know like usually BOD and COD, those are terms that used to measure the content like for the wastewater, like sewage treatment, water or industrial wastewater treatment. Those are two important like names or parameters that the first thing we will ask. What is the BOD and the COD? Now those are representing like how polluted is this water, like what's the biological oxygen demand, like how much bacterial load in the water, in the wastewater. So this BOD and COD should not be removed by reverse osmosis. There are other technologies to be removed. Again, I'm repeating myself, reverse osmosis is good to reduce whatever dissolved or suspended in the water, like sulfates, like bicarbonates, chloride, potassium, calcium, magnesium, and you name it, all those dissolved ions. Now, we will now start talking a little bit about how can we select some of those pretreatment, like for the reverse osmosis systems. Now, reverse osmosis systems is it has few terms before we talk about this one. Like we have like membrane rejection. We need to talk about it. It has also like some membrane surface area. It has like membrane, like the GFD or the flux, like how fast is the water going through this membrane. It has a term called the recovery, and it has a term called the permeate. And it has a term, the last one is called the brine or the reject or the drain. Brine, reject, they're all the same term. Now we'll talk about, just draw a little bit of
the balloon because it's so light in the can use the balloon.
Okay, use the. Now this is like a typical membrane drawing. So the feed water is going to come from here, and you're going to have a stream, which is the permeate. And we have another stream, which is what we call the reject. And we have what we say the feed. Now, this is like the membrane, how it looks like. That's how it looks like. Sample of the membrane. Now, this is what we say spiral wall membranes. Spiral means like when they cast the membrane, it's a flat sheet. So they bring like a long flat sheet, and then they cover it with a netting material, like a grid on top of it. Then they bring another membrane sheet, and another gridding material, then another membrane. And in the middle of that, they put something called a PVC pipe that collects the good water. And this pipe inside has little holes. It collects all the good water, the permeate water. Then they roll it. And at the end of the membrane here, they have like a little glue, and this is all automated because they control the thickness of the glue. So, and they roll it. And they come up with a thickness. There are 2 or 3 different types of membranes. There is a little one, which is the commercial. It's about 2.5 inch diameter. And there's another one, 4 inch diameter. And then the third one is 8 inch diameter. Now for the big jobs, they came up with a new 16 inch diameter, which is huge. You need a big forklift to lift this membrane. So the most common one in the water treatment industry for like industrial application is the 8 inch by 40 membranes. There is a lot of major membranes manufacturers worldwide, like Dow Film, Dechlorination, Toray. So most of those companies are here in California. Now let's talk when we feed the water. Regardless, it's the same theory. Whether it's a brackish water, tap water, seawater, it's all the same thing. So the water will be fed to the membrane, and it's gonna get pressurized through the membrane. How does it get pressurized? We need to control the reject by having a valve here. We cannot close the valve 100%, because if we close the valve 100%, we can foul the membrane. There are certain parameters to perform the design. So, and there's some design calculations, like based on what's the feed water analysis, how many membranes, what's the flow rate. So we'll talk about this a little bit because it's a lot of information. So when we feed the water here, some water is going to go to the reject, some water is going to go to the permeate. As a rule of thumb, each membrane should not exceed 12% of recovery. Recovery means what? If you're feeding water here, 12% of that should go here, and the 88% should come here. If it's one membrane. Now, if it's 2 membranes, we can go another 12%. If it's 3 membranes, we can go another 12%, so 36%. If it's another membrane, so now the higher number of membranes gives us a better chance to go with a higher recovery. So if the system is smaller, I mean, we are obliged to go for a low recovery. So now there's something called recycling. So what we can do, we can take this one here and have a little valve here and recycle a little bit of water here. That's what we call the recycled concentrate. So when we recycle the concentrate from here, we cannot do that for big quantity of water because this is a salty water. Again, there is a way to calculate this information, which is we should not exceed like big percentage. Otherwise, you're going to foul the membranes. There is again another formula to calculate all those things. We'll talk about it if you want later. Now, the permeate itself, the terminology of the permeate, it's the product of the RO, the good quality water that comes out of the reverse osmosis. Now, like if we take a look at the filters, we name it filtrate. It's like ultrafiltration and media filter. So the water that's coming, or the treated water, we call it the filtrate. In the reverse osmosis, we call it permeate. Permeate is like usually when you hear the word permeate, it means you would understand immediately that, oh, this is a good quality water. That's what's everybody has a common term for the industry. Now, some people would ask, what are we going to do with the reject water? What are the solutions? Now, reject water, if it's a brackish water, it's not going to be really bad. So you can throw it to the sewage, no problem. Now, if there are like some plants, they would handle TDS up to 5,000 ppm. So it depends which country this is going to. We can use it for irrigation purpose. Now, in some countries, the water is really, really scarce. And taking this water and passing it through another RO to minimize the wastewater that's going to go to the waste, to the sewage network, or back to the sea or whatever, it's feasible. Treating this water for sure is going to be way cheaper than treating the seawater because the seawater has a way higher salinity. So many countries now they're starting, including us here in the US, they would take this water and we would pass it to a second reverse osmosis system. When you do something like this, you would increase the overall system recovery. Sometimes we can go with the projects where we can achieve up to 93 or 94% overall recovery. That means if you are feeding like 100 GPM here, you would get a reject of maybe 5% of that, which is really good because we're talking about really high salinity water. It's not only high salinity, which would have a lot of other substituents in the water, which is really difficult to treat and hard to treat. It's just you would have a lot of high hardness, high bicarbonates, high alkalinity, high, you name it, everything in the water is going to be 10 times, 20 times, 30 times. It's you go up to 90 times. So it's really concentrated water. That means if you start with 1,000 ppm here, you're going to end up having 60, 70,000 ppm or 80,000, which is really crazy high. Okay, now we talked about the membrane structure. Those membranes, like we said, spiral wall membranes, they don't like chlorine, they don't like heavy minerals, they don't like oil, they don't like organic. So we also talked about the definition of the terms, the main keyword that we usually use when we design reverse osmosis or when we select the reverse osmosis. We said feed water, we said permeate or the product water, we said reject or the drain water. Another term we said the recycle for the concentrate or the concentrate reject recycling. So this is another term, but a lot of people they use it when they select or design a reverse osmosis system. Now let's take another typical example for reverse osmosis in general. I'm going to take a brackish water system, how the water would work. So we have a storage tank where we have the water is coming here. So we're going to need a pump here to pressurize the water to go to the RO. Here is the RO, which is a reverse osmosis system. Now the reason why I left a gap here because we're going to have some equipment here to protect the RO. That's what we say, or what we name as a pretreatment. Pretreatment is like a preliminary treatment before the reverse osmosis. So those equipment are necessary, and we're going to explain. So we're going to start with whatever we call media filter. Then we're going to go to, let's say, a carbon filter. And then we're going to go, let's say, for a softener. Usually there is a brine tank for the softener. And then we're going to go for the RO. Okay? And then after the RO, we're going to go to a storage tank. And then we're going to go for a distribution pump and a UV, and then to use. Now this is a very common example for typical commercial reverse osmosis system that everybody would like to have to treat the water, make sure the water is safe to drink. Now let's assume that the TDS is anywhere between 1,000 to 2,000 ppm, which is easy to treat because the salinity is in the lower scale. Now why do we need a media filter? We're gonna have in the next session we're gonna have a deep discussion about the media filtration, but preliminary it removes suspended solid turbidity, it removes any oxidized iron, manganese from the water. Why do we need carbon? So if we assume this is a city water, or if we know that there is any oxidized minerals, or if we know there is like a little bit of viruses and bacteria, it's important that we should dose some chlorine. Okay, chlorine means is like it's an oxidizing agent, which is a cheap oxidizing agent, and it does the job. It's going to oxidize the iron, it's going to oxidize the manganese, it's going to get rid of most of the viruses and bacteria. Okay, so we assume that there is a chlorine in the water now. So the media filter is going to get rid of the turbidity and suspension solids and any oxidized heavy minerals. The carbon filter is going to get rid of organic, and it's going to get rid of the chlorine that's not being utilized by reacting with the bacteria and the viruses and oxidizing the iron and the manganese. So you're going to have some extra chlorine. So, like what we said earlier, we cannot allow any chlorine to go to the reverse osmosis. Chlorine would damage the membrane if you kept it running more than 1,000 hours. So we need to prevent having the chlorine to go inside the membrane. Carbon filter would remove, like what we said, the chlorine from the water. Softener. What's the benefit of a water softener? Water softener is an ion exchange technology or process that makes an ion exchange between different ions. Like some ions you don't want it to be because it harms other equipment, or you don't want it to be in the water for one reason or another. Example, like calcium and magnesium, that's what they cause the hardness in the water. So we're going to get rid of them. In this case, calcium and magnesium is what we call the total hardness, is going to follow the RO membrane, which is this one. So we're going to get rid of it. So we exchange here. We release the sodium and we take out the calcium and magnesium. So that's why we call it ion exchange. So softener again, it's good because like traces. I don't want anybody to understand that we are putting the softener to remove the iron here. No, it just in case if the media filter would remove 99.5%, if you have a little bit of iron traces, the softener is going to get rid of it also. So it's a good pre-treatment for the reverse osmosis. Now we get rid of the suspended solids, we get rid of the chlorine and organic, we get rid of the hardness. So now we are ready to feed the water to the reverse osmosis, that's why we're talking about the whole subject is reverse osmosis. Now, the big challenge is the reverse osmosis is going to reduce the TDS, that's what we want. TDS, viruses, bacteria, and all those things, if whatever left over from the water. Now, the RO is ready to accept this water, and hopefully everything is going to be good. The design is good. So you're going to get like a water. If we assume that the water here is about, let's say, 2,000 ppm, so you're going to get a good clean water, which is way, 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 way better than a bottled water or than the city water. It's excellent for drinking, excellent for the food, for cooking, for car wash, for industrial applications, for chemical process, for you name it. So whatever industry you want to be on, the RO water is excellent application for it. Now the water is going to be stored here, like in this storage tank. Now you can ask you a question. How much time this water is going to be stored in the tank? Is it an hour or 2 hours? Okay, I'm going to use it, so it's okay. There is no need to do any chemical dosing here, which is a chlorination. If you think that the water is going to stay more than 24 hours in the tank or whatever, you need to dose a little bit of chlorine to prevent any upcoming bacterial growth in the water. Otherwise, remember, this is going to be a very clean water, really, really good quality water. So when the water is really, really good quality, a lot of things that's going to start coming to the water because it's really clean. It's going to start taking bacteria, viruses. It's going to start taking some gases from the air. So you want to prevent something like this. So you would dose a little bit of chlorine, like maybe 0.2 ppm. Now, if you don't want to use the chlorine, some people will say I don't want to use chlorine. We would suggest to use the UV. Now, the good thing about the UV and the bad thing about the UV at the same time, UV is excellent because it's natural. It doesn't have any chemicals at all. So the way how it works, it just hits the DNA of the cell and destroy it, there's no more bacteria. While the chlorine, the good thing about it is it's like it has a residual. Residual, that means if there's any upcoming bacterial growth, the chlorine is going to be ready to attack it. While the UV is good for instant applications, good for instant use. So, but it doesn't leave any residual, like reserve to treat or kill any upcoming bacterial growth or viruses. So those are the difference between the bacteria and the growth. So I'm going to end up my session about the reverse osmosis now, about talking a little bit about the instruments that we're going to use to control the reverse osmosis. To control the reverse osmosis, we need some pressure gauges, we need some flow meters as a minimum like requirements for and we need what we call control panel. Control panel would control starting and stopping the system, protecting the pump and the motor, showing the quality of the water. That's the basic things in there, and closing the water when the system is off. Now, the flow meters would let you read how much water you're getting in each stream. Remember, we talked about feed water, we talked about product, we talked about reject, we talked about the recycle. We usually need to measure 3 out of the 4 because if you add the 3, you would know what's feed. So we need to have flow meter for the product or the permeate, the reject or the drain, and the recirculate. Recirculate, that means we take a little bit of branch from the reject and send it back to the feed of the hour. So those are the instruments that we have to use for any basic reverse osmosis system. And the last thing is we need to have a TDS or conductivity device to tell us that this reverse osmosis is working or not, which is it treats the quality of the water that's produced here in a matter of ppm or conductivity. Like in a case like this, if you have a 2000, you would get like something below 12 or 15 ppm, which is superior quality water. So we're going to end up this session now. So after a few minutes, we'll start with the next session. Thank you.